In this video, we will cover the transition complex stereoisomers. Now, stereoisomers, there are two types in A levels. The first one is called the geometrical, also known as cis-trans on the left-hand side. And on the right-hand side, we will look at the other part called the optical, also known as enantiomers. All right. Now, I'm going to cover 5 types. All right. 2 for geometrical and 3 for optical. Now, I'm going to teach you the representation, all right, so-called the formula. Now, capital M indicates metal, okay? Now, anything that is small alphabet, like alphabet A, alphabet B, small letters indicate monodentate, okay? And then if you look at the capital AA, okay, capital AA means bidentate, okay? Now, so I hope by now you would know what is monodentate, bidentate, and polydentate. Okay, now maybe I just quickly go through the definition with you. So monodentate ligand is defined as a species that can donate one lone pair of electrons to a metallic atom or ion via one coordinate bonding. Okay, that is monodentate. So what you want to focus here is mono means one lone pair, one coordinate bond. Now, if bidentate ligand, all you need to do is you change the word here to 2 lone pair of electrons to form 2 coordinate bonding to a metallic atom or a metallic ion. Okay, polydentate is more than 2. Okay, so maybe you want to underline, all the underline you change to 2. And for polydentate, more than 2. You just fill in the underline, you change accordingly. Okay, now, so therefore, A and B, okay, A and B are small a, small b are monodentate. Capital AA means bidentate. Okay, now, can you see the bullet point up here? All right, just in case you forget, anything small capital, mono, double capital A is a bidentate. Now, capital B means it's a different bidentate, all right? Now, the first one I'm going to cover is a cis-trans, quite basic, okay? A2B2. It means that you got 2 monodentate of type A and 2 monodentate of type B. That means A and B both are monodentate but different type. So I'm going to take your actual pass here, okay, to draw the complex, okay? Now, so let's look at this question, okay? Platinum forms a complex ion with the formula given. In this complex ion, the carbon atom of each cyanide ion's ligand bonds to the platinum ion. This complex shows stereoisomerism. You have to decide what stereoisomerism. Is it cis-trans? Is it optical? If you see the formula of the complex having A2B2 type, then you know they will form cis-trans isomerism. Draw the structures of these 2 isomers in the box below. All right, so they will form a square planar shape complex or square planar shape complex. Okay, so how do we draw this? Okay, because you only have 4 ligands around you. When you have 4 ligands around you, you have 4 coordinate number. Your coordination number is 4 coordinate, okay, coordinate number Okay, then it brings us down to what is coordinate number or what is coordination number. All right, coordination number is the number of coordinate bond form. Okay, you only have 4 ligands, so you have 4 coordinate bond forming around you. And when you have 4 coordinate bonding around you, right, you can have 2 types of shape or geometry. The first one is square planar, the other one is tetrahedral. Okay, but normally A2, B2 will be in a square planar in your syllabus, unless stated otherwise. If you have an A2, B2, okay, normally in square planar. So first, we would like to draw a square plane. Please draw in 3D. Then you have the wedge wing, and you have the dotted line. Okay, I will just quickly draw the other side, because you have to draw 3D. Stereoisomers, they have a different orientation in space. So that's why you need to ensure that all drawing of transition complex must be in 3D shape by default. Okay, now your cyanide lone pair, okay, it's on the carbon, okay, because the carbon is the one who donate the lone pair into the platinum. So make sure you point the bond to the carbon, not to the nitrogen, okay? And then chlorine is 1 atom like this. Okay, now when you have both 90 degrees apart, okay, if your 2 monodentate is 90 degrees apart, we call this cis-isomer. If you draw it the other way around, which is opposite, this is 180 apart. This is called trans isomer. Because if you fill in the 2 chlorine, they are also 180 degrees apart. The relationship between the 2 ligands. So this is a cis-trans isomer. Okay, yeah. Now, one more thing to add in your syllabus, you have to know that cis isomer, okay, which is the cis platinum, this is this formula, PT, this one here, okay. Now, whether is it polar or non-polar for the cis version, I don't think it's platinum, yeah, okay. Now, is this complex so-called polar or non-polar? So I'm going to write on the left and on the right-hand side. Okay, now, first we look at where are the 2 cyanide and where are the 2 chloro, okay? So maybe you do not know who is more electronegative, but I know that chlorine more electronegative, chlorine more electronegative. So you have a net direction of the dipole moment, okay? And as well, you also have cyanide pulling and cyanide pulling. So therefore, here also you have a net direction of the dipole moment. But the question now is, we do not know whether in net total, would the top dipole be stronger than the bottom dipole? Okay, but nevertheless, we know it's towards upward or downward. Okay, so therefore, this is a polar molecule. Whereas on the right-hand side, for your trans isomer, okay, your 2 chlorine with the same electronegativity, their dipole moment will cancel off each other. And for the 2 cyanide, with the same electronegativity, the dipole moment also cancel off each other. Hence, we know that this is a non-polar complex. All right, so polar, non-polar will determine what is the intermolecular forces that your complex will form with another complex. Right? So therefore, this is the first example of having a Ma2B2 configuration. All right, they have a cis-trans isomerism in a square planar shape. Now, we shall go to another example, very similar. Okay, do you identify the formula given, which is small a2, small b2, bromine is mono, cyanide is mono, and you have a transition metal called capital M, which happens to be nickel here. Okay, so when you look at the configuration, you know that this is cis-trans. Okay, so therefore you can fill in the blank. Okay, over here, you draw your square plane. I will always have a good practice of drawing the square plane so that it is very clear that the two wedge wing is pointing to the audience and the two wedge, the dotted line is pointing to the audience. Sorry, backstage is dotted line, wedge wing is to the audience. Okay, now you can draw your cis-trans. Okay, so for example, bromine, I put here. Cyanide, remember the cyanide is the carbon that has the lone pair that is donating into the nickel. Okay, so you make sure you point the bond to the carbon. Okay, so this molecule is a cis isomer. This molecule is a trans isomer. Type of stereoisomerism, you answered geometrical. Or you can answer cis-trans. Okay, so I've covered the first one called Ma2B2 in a square planar shape because you only have 4 things. So 4 things, you either bear a square planar or you bear a tetrahedral. Okay, but mostly A2B2 is square planar. Now, the second example of stereoisomers that I'm going to cover is on a octahedral shape. All right, why octahedral? Because there's a total of 6 ligands. Okay, there's a total of 6 ligands. Can you see A4B2? Okay, octahedral shape. All right, now, so for a A4B2, okay, we want to focus on the B2 because that 2 can align in cis or trans. Okay, so let's look at this particular question taken for winter 23. So they've given you nickel with a diaqua and tetraamine. Okay, so you want to focus on the one that is 2. And in this case, your aqua is the 2 that you're going to focus on. Okay, so your 2 aqua can achieve, align in a cis or a trans format. So first, we want to draw the basic structure of an octahedral out and draw it in 3D. Okay, now your H2O, we would like to draw cis. Okay, so maybe I would like to draw cis like this. Make sure the bond is pointing to the O because the O is donating the lone pair. Okay, this is called cis. Why? Because the relationship between the two aqua is in 90 degrees. So long you're 90 degrees apart, you are cis. And you fill in the rest with the amine, okay, or ammonium. So make sure the nitrogen is the one pointing to the bond. Must be very clear like this. So this is your cis isomer. Now let's do a trans. Okay, now trans for the diaqua, can you see my oxygen is pointing to the dotted line? Because oxygen is donating the lone pair, must be very careful. So this is 180 between the 2 ligands. Okay. I just realized I put degrees Celsius. All right. Now, and then the remaining one, you put your amine in. So we'll focus on the 2. Okay, and this is your cis-trans isomerism. Okay, now then add on which one of them is polar. Only focus on the 2. Okay, only focus on the 2. The 2 aqua on the left does not cancel off each other. They have a net direction of the dipole moment 45 degrees in between the 2. Okay, like this. So that means this is delta negative and this is delta positive. So because the dipole moment does not cancel off each other for the 2 water molecule, so this is a polar molecule. On the right, the 2 water molecule cancel off each other. This is a trans molecule. and therefore it is non-polar. Okay, because dipole moment cancel off each other. So this is the second type, right? MA4B2, we focus on the B2, right? Now I'm going to change to the third type of stereoisomerism, where we start to involve bidentate, which is capital letters. So when you have AA, means it's bidentate in capital letters, not small. Okay, now, so let's look at this particular question. You look at the configuration, so-called the format or formula, M capital AA, 3. That means you got 3 bidentate. Okay, 3 bidentate. Now, a bidentate is defined as a species that can donate 2 lone pair of electrons. That means one bidentate will donate 2. They will clamp at 2 locations. Okay, so when you have an octahedral shape, that means you got 6 positions. One ligand take 2 positions. So 3 ligands will take 6 positions. That's how they complete the 6 position on the octahedral. So your ethane 1,2-diamine, which is a very common bidentate that you need to know. In short, they are known as EN. Okay, but please don't go and use EN, but normally your examiner will allow you to use EN. They will say you may use EN to represent ethane 1,2-diamine. They'll normally allow you, but please make sure they use that sentence. Okay, now you must know the formula of your ethane 1,2-diamine, or also known to me as ethylene diamine. I'll normally use ethylene diamine. Ethylene diamine. The spelling is somewhere around there. Ethyl, without the E. Okay, ethylene diamine. I'll normally use ethylene diamine, all right, instead of ethane 1,2-diamine. It's faster, ethylene diamine. They are the olden way of naming the compound. It's the same thing. Okay, please know what is the formula of your ethane 1,2-diamine, also known as ethylene diamine. Please know. Okay, now, so first, you can see they form this complex over here. So your vanadium has 3 ethylene diamine or 3 ethane 1,2-diamine. Okay. Now they allow you to use, watch here, this structure to represent your ethylene diamine. Okay. Now I'm gonna teach you the very correct, conventional, traditional way to properly draw the structure without using any representation, so-called the trapezium shape there, as you can see. Okay. Now, ethylene diamine, you can clamp at 2 positions. Now, you can randomly clamp any 2, but there's only one rule. You cannot clamp opposite of each other. Apart 180 degrees cannot. Okay. So you can see here, the nitrogen here and the nitrogen there. These are the 2 lone pair that is gonna donate their lone pair in to the transition metal. Okay, and then it's actually NH2. If I were to draw full structure, skeleton formula. Can you see actually they allow you to make it simple in skeleton formula? Okay, but I'm going to draw one full-fledged without using skeletal. Okay, so for example, I always use the trapezium shape here. As you can see, it's like a 4 corners. Okay, I'll normally call it as a trapezium shape. Okay, so you put an N. Okay, what you can do is you can draw the trapezium shape, okay, with 4 corners, and then you put your 2N and your 2C here. Then you fill in the blank. Make sure it's bonded to the nitrogen. So you can see that it totally clamped in, okay, at 2 positions. So this is 1 ethylene diamine, okay. Now, then you can also clamp it here. I draw the 4 corners, 1, 2, 3, 4. It's like the trapezium shape like this. Make sure your bond is bonded to the nitrogen. Lastly, here, 1, 2, 3, 4. Okay, then this is CH2. This is CH2. Okay, now you can see that this is how I draw the 3 ethane 1,2-diamine on your vanadium ion. Okay, now, as much as you have the freedom to clamp anywhere you want, there's only one thing that you can't do, which is opposite. For example, please do not clamp top all the way to the bottom. Like this. You don't do this. All right, because the angle between the two corners of the ethylene diamine is 180. Okay, so it's too small to stretch them apart 180. When you only have 4 atom length, actually they only have 4 length, NCCM. 4 atom length is not sufficient to stretch 180 apart. Not wide enough. But if you align according to my drawing in isomer 1 box, you realize that you only clamp and their angle between the two corners is actually 90. Can you see? Okay, I only can stretch the 4 atom length to 90 degrees. They're all 90 here. Okay, they're all 90 degrees. Okay, so please do not clamp 180 apart. Okay, so 180 apart can be top, bottom, like this. You also cannot clamp this way. Okay, it's the same thing. All right, you also cannot clamp this way. This way you want to clamp it this way, also cannot. Okay, they are too short to clamp 180 apart. So this is a forbidden thing. All right, so I've just drawn one isomer to show the 3 bidentate. Now, for your information, when you have a 3 bidentate, automatically your type of isomerism is optical isomer. Okay. So optical isomers, do you still remember how to define it? It's mirror images of each other and are non-superimposable. So when you draw one on the left, you just need to mirror effect them. Just imagine there's a plane of mirror here and you reflect it. Okay, now this time when I reflect it, right, I will use their skeletal formula, the short form version, because they said you may use. So I will use it. The first example, I did not use it is because I want to show you how to draw the full-fledged, just in case they never give us the quote, you may use. Okay, but if they give you may use this, then of course we will do the easy way out. Okay, so I would like to reflect my drawing by using the short form version. So this is the mirror effect, but a more neat, more simplified version because they allow me to use a short form skeletal formula, so-called the trapezium shape, to represent the ethylene diamine structure. Okay, and it is mirror effect, as you can see. So the type of isomer shown, okay, is optical isomers. Okay, so that is your 3 bidentate format. So when you have a 3 bidentate, automatically it's optical isomers. All right, now let's go to another example here. Something not familiar. Okay, it's okay, but they did say above the question, all right, they did say, and in fact, they say you may use, all right, you may use CCN, so-called a skeletal formula, but actually to represent your BIPY. Okay, so BIPY over here is also a bidentate. Okay, not in our syllabus, but it's fine. Okay, because they already allow us to use and they already tell us that it's a bidentate case. All right, so did you recognize that this is a capital M, okay, with a bidentate 3 version? So if you have a 3 bidentate version, automatically you will show it optical isomerism. So this time I will use the conveniently the shortcut way. Okay, draw a plane, draw the triangle, dotted line. Okay, then you can clamp. Okay, let me just see just now how I clamp on the left so that I do something different. So when I clamp it this way, so now I'm going to clamp this way here on the left. Okay, then no choice, this one I have to clamp here. And this one I clamp here. Like this. Okay, and then you just flip the mirror image to the other side. In trapezium shape, I normally refer this to the trapezium shape. I clamp in, all right? Bidentate can donate to lone pairs in, all right? So this is the optical isomer. You can answer down here. So this is the third type of so-called way, okay, on what are the possible questions that can come out in the exam, okay? Now, if you want to do a remix between your cis-trans and optical, we already covered cis-trans and optical already, just so you know, okay? And if you want to do a remix version between the cis-trans and optical, it's a can, all right? Therefore, you will have to see this kind of a format where you got a 2 bidentate and 2 monodentate. Now, capital AA is a bidentate and you have 2 of them. So 1 bidentate will donate 2 lone pair. 2 bidentate will donate 4 lone pair. That means they use 4 out of the 6. And then you realize you have a small letter B and you have 2 of them. Okay, so your B and your B donate 1. So total you have 6 position on the octahedral shape. Okay. All right. Okay. Now, first, okay, I would like to give you a tip. Okay, to show optical isomers, okay, you must have minimum 2 bidentate. Okay, you must have minimum 2 bidentate. Just now the first one was 3 bidentate. They already achieved the minimum called 2. Of course, they will show optical isomerism. For this example here, this one has 2 bidentate. They already achieved the minimum, hence they are able to show the optical isomerism. But you also realize the small letter b will show cis-trans, isn't it? So this part will show the cis-trans. And the minimum 2 bidentate will be responsible to show the optical isomerism. Okay, but it doesn't mean cis-trans got 2, optical got 2, means they are total 4. Obviously, it's not 4, because as you can see this particular question, they only draw 3. Okay, now cis-trans definitely is the 2 among the 3 here. Okay, so we want to focus on the monodentate, which is the small b. If you look at this question, your oxalic ion here, C2O4, okay, another bidentate that you need to know. Okay, so there are 2 bidentate that you need to know in the syllabus. The ethane 1,2-diamine or diamino, and then the other one is the oxalic ion, also known as ethane dioic ion, which looks something like this. C2O4, 2 minus, is your oxalic ion or your ethane dioic. So they are having this structure. Can you see it's also 4 atom length? OCCO, and they clamp in is your bidentate. Okay, so normally the short form for oxalic ion is known as OX. But your examiner would normally say you may use OX to represent. Okay, it's not for you to use. Okay, so ethylene diamine is EN, oxalic ion is OX. Okay, don't go and use it until your examiner say you may use it. Okay, so you can look at the 2 bidentate is your oxalic, also known as ethane dioic ions, and your monodentate is your aqua. So we're going to quickly draw our cis transfers. Okay, so I'm going to draw my cis. Square plane, this square plane is not mandatory to draw, but I prefer students to draw because it makes your drawing looks very neat. Okay, so make sure you point to the O. Okay, can you see my H2O? I point to the OO, and then the remaining, okay? Now, over here, they never say you may use any short form to represent, right? Now then, unfortunately, you have to open up the structure. So I'm going to go in, okay? So this is my oxalic ion bidentate. Okay, and I will use a simplified version. I really draw the whole molecule out. Same, you can see it's a 4-atom length. Right, they will clamp in. There you go. This is your cis version. You focus on the 2 monodentate here. This is a 90 degrees. This is your cis isomer. Okay, focus on the 2 monodentate. Then, of course, you can draw your trans isomer. The bond is pointing to the oxygen. Okay. Okay, this one, 2 water molecule, 180 apart. This is called a trans isomer. Okay, so I already settled the cis-trans part of the formula, which is the B2 over here. Now then we're gonna handle the bidentate, because when you have minimum 2 bidentate, you can show optical isomerism. So therefore, the correct way to go is you take your cis, you mirror effect, you take your trans, you mirror effect as well. Okay, but then obviously, we only take the cis to mirror effect. Okay, we don't take the trans. Now I want you to look at stereoisomer 2, which is the trans drawing of mine. If you take stereoisomer 2, which is the trans, and you mirror effect it, it will look exactly the same. All right, so no point doing a optical on your trans isomer. You can only do, okay, the optical for your cis isomer. All right, so everybody, I'm going to take my isomer 1 now, and I'm going to flip it to the right-hand side, which is the mirror effect. I'm going to draw it down there. Okay. I'm drawing the right-hand version of it now. So now, can you see the 2 water molecule? Okay, it's on the right hand now. Okay, so this is the optical isomers for the cis version. Okay, so when you have a 2 bidentate, 2 monodentate combination, they will show cis-trans and optical, but bear in mind, only the cis will show optical. The trans won't show optical because the mirror effect of the trans is exactly the same thing as the original version. Okay, so normally they come up 3. Can? Okay, so this is the 4th type of question, which is the M capital AA2 and a small b2. Yeah. Now, similarly, again, let's look at this question here. Now, they show you that this formula is geometrical and optical. Thank you. So nice. Okay. Now, what is ED? Now, ED is not in our syllabus. Okay. But we can clearly know that ED is a bidentate. How to know? Can you see that you may use this? Okay. They gave us the shortcut, and this shortcut already tells us that ED is a bidentate ligand that can clamp to position. So we recognize that this is a M AA to B2 type of transition complex formula. So we know that they will show cis-trans, CT in short, and the two minimum bidentate will show the optical. Okay, so same thing, you draw your cis and draw your trans with respect to the two monodentate, and in this case, your monodentate here is your chlorine atom. So you can draw your monodentate here, chlorine and chlorine. Okay, now if you want, you can connect it for your square plane if you want. Okay, but normally I have a habit to do that, but it's fine if you don't want to draw. And then the ED, we can use the short form, okay? So therefore, we have to do something like this, O. Okay, it's a 4-atom length. In your syllabus, normally they'll give you the 4-atom length version, okay? So I put the chlorine now in a trans, 180 degrees. This is trans. This is 90 cis. Okay. Now then the remaining. Your bidentate will always clamp 90 apart. Okay, they cannot clamp 180. 4-atom length can't clamp 180 apart. Okay, so the left is your cis isomer. The right is your trans isomer. Okay, now then you take your cis isomer, okay, and you do a mirror effect. You can flip it to the left, you can flip it to the right for the mirror image, up to you. Okay, so I'll leave it to you for the third drawing and the last one. Okay, so that is the capital AA2 and B2 format. Okay, okay, now the last one here, okay. Now let's look at this type of formula. MA3B3, small a, small b, means what? Monodentate, 3 of them. Monodentate, 3 of them. Okay, so 3, total got 6. Same thing, it's in octahedral shape. Okay, octahedral shape. Okay, now, so you can see you have 3 ammonia and 3 chlorine atom. Okay, now, you can draw them. Okay, so I teach you here. I draw the square plane first. Must draw wedge and dotted line. You don't have to expect them to tell you draw 3-dimensional diagram. Okay, normally they will do that. But if they never say draw 3-dimensional diagram, you also have to draw, because stereoisomers, they have different orientation in space. Space means Marshall 3D. Okay, now, so the 3 ammonia and the 3 chlorine, right? How do we arrange? Okay, of course, this is like a new type. Now, MA3B3, okay, is actually another form of cis-trans. Okay, they are another form of cis-trans. At the starting of the video, I did show you cis-trans got 2 type of combination. Okay, you have the A2B2 and you have the A3B3. Okay, now, so the A3B3, right, you want to align them in 90 or 180 apart. So I want you to look at the 3A, okay, which is the 3 ammonia here. All right, so the 3 ammonia first. Okay, I would like to draw the 3 ammonia in this way. Okay, why this way? Okay, why this way? Because when I connect any 2 ammonia, they are 90. Now the top and the back is 90 degrees apart. The top and the front is also 90 degrees apart. The back and the front is also 90 degrees apart. Any 2 you pick among the 3 will always be 90 degrees apart, isn't it? Okay, yeah. So therefore, we can draw a triangle, but this is for me to show you, but you don't draw in your exam, okay? This is for the explanation part. You can draw a triangle to connect these three nitrogen, and you get a face of triangle here, isn't it? Okay, one face of the triangle. Then, therefore, you fill in the rest with the 3 chlorine. Now, same thing, the 3 chlorine, right? You pick any two. Are they 90 degrees apart? Yes. If you pick the front and the bottom, it is still 90 degrees. If you pick the back and the bottom, it's also 90 degrees apart. Okay, so pick any two among the 3, they are 90. Okay, and then I would like to draw for you. Okay, we're going to connect the 3 chlorine atom, and you will see a face of triangle down. So you have one face of triangle up, you have another face of triangle down, like this. Okay, so the actual name for this isomer is actually called facial isomer. Actually, okay, we call this fac. Okay, facial. It comes from the word facial. Okay, the actual true name for this isomer is called fac. Okay, because we do see two faces of triangle in this drawing. Okay, now therefore we move to the next one. The next isomer, okay, obviously you need to have a 180 a partner, 180. Okay, so for example, I draw my ammonia, ammonia, and ammonia here. Okay, now then what I do is I connect my 3 ammonia. What you can see here is that between the top and the bottom, you have a 180 relationship. But top and the plane, 90. Plane and bottom is 90. Among the 3, when you pick one, not to say any 2, you pick 2, maybe that 2 can be 180. So long you have a 180 angle apart, then yes, this is called a so-called the trans isomer. All right, I got 290 and 180, right? Top plane 90, plane bottom 90, top and bottom 180. When you have 180 there, that means it's the trans isomer already. Okay, now if I connect the 3 nitrogen atom, you can see it's like a half circle, half moon. Okay, it's like the Earth meridian line. Okay, meridian, the straight line. Okay, half meridian. Okay, the line. Okay, now and the remaining 3 chlorine here, you have to sit here. And if I were to pick any 2, so let's say this chlorine, back and front, they are 90. But the front and the other side back is 180. The minute you have 180, right, that means this is the trans version of it. Okay, and if you were to connect these 3 chlorine, you can see there's a half circle again. So one half circle is standing up, and the other half circle is flat. Okay, so it's also another plane, which is a meridian line. Okay, so therefore, because of the meridian, the name for this isomer is actually called mer. Okay, we call this mer-fac isomerism. In actual case, this is called mer-fac. Okay, mer-fac isomerism. The true name for this is actually called mer-fac isomerism. But because mer-fac is not taught in A levels, right? They tone down the name from mer-fac to cis-trans U. Okay, so cis or facial is all 90 degrees related. Okay, so if you want, I tone down the name to cis. Okay, which is what your past year has been asking. This is the cis version. Instead of answering mer, you tone it down to your version called trans. Because trans confirm got 180. Cis, you won't see any 180 between the same ligand. You look at the 3 ammonia on my left drawing. The 3 ammonia, you will never see a 180 relationship between the ammonia. You look at the 3-chlorine on the left drawing, you will never see 180. If you don't have 180, you are a cis version. But the true name is actually called phase because they have 2 faces of the triangle. So what is the type of stereoisomerism? You answer cis-trans according to the partial marking scheme. Okay, cis-trans. Now, if you want, you can also answer mer-fac. Okay, you can do that. Okay, yeah, you can do that actually lah. All right, because that's the true name. You want, you can answer mer-fac, but you won't see the mer-fac in your marking scheme because it's not in your syllabus. So now you know your syllabus will ask things that, your passing will start asking things that's not in your syllabus. Okay, yeah. So that is the last example, which is MA3B3. Of course, there is another pass here. Okay, they came out. Okay. Now we always want to look at the configuration of the complex they given to us first. But of course, student needs to know whether are you mono or are you bidentate. Because in exam, they won't give you capital M, capital AA, or small a, small b. You need to look at the true molecule and decide whether is it a mono or bidentate. Okay, so first, ammonia, we know that this is a monodentate. All right, so it's a small a and you have 3 of them. Now, NO2, okay, NO2, because student not sure. That's why it's very fair that the examiner say that your nitrite all right. Okay, so your ammonia is a monodentate and your nitrite ion, which I believe many students do not know, all right, it's a monodentate, but it's fine because the examiner told you that your NO2 negative ion is a monodentate. So this will be your small b, and you have 3 of them. So when you see A3B3, you know it's a cis-trans isomerism or a mer-fac isomerism. Okay, remember cis all 90, trans must have 180 apart. Okay, so let's quickly draw the 2. Okay, so maybe this time I will draw something very a little bit different. Okay, I'd like to draw the 3 ammonia here. Make sure it's pointed to the nitrogen atom. Okay, so this is the 3 ammonia. All right, and if I connect them, any 2 among the 3, you ask what is the angle, it will be 90. Okay, so can you see there's a face of triangle here? It's like a pizza, all right? The pyramid that you can see. So this is 90 degrees. And of course, the other 3, it's on the N, not on the O. The lone pair is donated by the nitrogen atom. Okay, by the nitrogen atom. So it's NO2, like this. Okay, and if you have to connect the 3 nitrogen here, okay, you will see the triangle is downwards, but it's to behind, right? It's behind. This one is right to our face, okay, standing upward. The other one is back, okay? So there's 2 faces of triangle. We call this the cis isomer. Okay, also known as fac isomer. It comes from the word facial. Okay, 2-face facial. All right. Then now you can draw the other one. Wedge and dotted line. Okay, so this time I draw the 3 ammonia here. And then you can see there's a 180 relationship, right? So this is the half moon, the meridian line. Okay, and then the other 3 chlorine like this. It's on the plane. It's still a meridian line, half moon. Okay, so type of isomerism, you can answer cis-trans, or you can answer mer-fac isomer. So this is the trans according to your A-level version, they tone down for you, but the actual one in chemistry is called the mer, from the word meridian line. Okay, all right. So now, if we were to go back, okay, to the starting of the video, stereoisomerism, okay, I've covered 2 types and 2 formula for the geometrical isomers and 3 formula for the optical isomers. And of course, the so-called the one I'm highlighting now, as you can see, the capital AA2 and small b2, that one has a mixture of a cis-trans and a optical isomerism. Okay, yeah. Now, I also, before I end, I just want to show you, give you a table. Okay, so far, according to A-level syllabus, right, you all would know square planar and octahedral. Okay, you can build your chart diagram. For example, the starting of my video, I actually build my chart diagram according to the type of stereoisomerism and what is the shape that they have. But this table here shows that I open my chart diagram where my stereoisomerism, I would like to split up into square planar and octahedral. So square planar will have what type of formula and maybe it's cis-trans, and then octahedral will have what type of formula and they have cis-trans or mer-fac or a mixture of cis-trans and optical. Okay, up to you on how you want to look at it. Okay, but in total I have covered 5. Okay, you just need to know these 5 and you're good to go. All right, and I'll see you in the next video.